Good morning, students. Now we are going to continue the concept that are dealt in the previous classes, like temperature dependence of resistivity. What is temperature coefficient of resistivity? It is especially for conductors and for semiconductors. And what's the another way for the learning temperature dependence of resistivity? Resistivity of a material is found to be dependent on temperature. Different materials do not show same dependence on temperature. The experiment reveals us that for a wide range of temperature, the resistivity of the material changes. If we increase the temperature of a conductor, the resistivity also increases. This we can learn from an expression showing the resistivity of a material at a particular temperature is given by rho naught into 1 plus alpha into T minus T naught. Here rho T means resistivity of a material at a particular temperature. Rho naught is the resistivity of a material at some reference temperature, usually it is 20 degrees Celsius, and alpha is the temperature coefficient of resistivity, and T and T naught are the various temperatures where T is at any temperature, any particular temperature, T naught is the temperature known as reference temperature. Now from this expression we can derive what is alpha, that is coefficient of temperature resistivity, that alpha is equal to what? So let us bring this rho T is equal to rho naught plus rho naught into alpha T minus T naught. So let us bring this rho naught to left hand side. Rho T minus rho naught is equal to rho naught into alpha T minus T naught. So let us write an expression for what is alpha is equal to rho T minus rho naught divided by rho naught into T minus T naught. Here see this rho T minus rho naught means change in resistivity that can be expressed as delta rho, nothing but change in resistivity, and divided by rho naught. T minus T naught is the change in temperature, it is denoted by delta T, and this is the expression for what is alpha, temperature coefficient of resistivity, that is alpha is equal to delta rho by rho naught into delta T, and its SI unit is per degree Celsius, per degree Celsius. See, this alpha value is variable, that means it varies for it depends upon the nature of the material, if it is conductor or it is for semiconductor. Now let us learn what is the alpha value for conductors. You know, alpha value will be positive for conductors, because if we increase the temperature of the conductor, of any conductor, the resistivity also increases. So alpha is positive for conductors. Why does this happen? Why this alpha value become positive for conductors? Because when we increase the temperature, the average kinetic energy of the electrons average kinetic energy of the electrons in the conductors increases, and thus resulting in frequent collisions, number of collisions becomes more, and so the resistivity also increases. Now if we just represent graphically, taking alpha, that is T, absolute temperature along x-axis, and resistivity which is in ohm meter along y-axis, we may find a graph for a, it will be non-linear for a small range of temperatures, and it will be linear for the wide range of temperature. You may see this is the linear change for a wide range of temperature, and this part is non-linear for a very low temperature. So if we want to highlight it and learn that behavior of certain materials at low temperature, the resistivity shows a non-linear change. Taking as usual, then it will be like this. So we can also, using this concept, we can find out the temperature coefficient of resistance also, since resistivity is proportional to resistance. We can, by using the same concept, we can find out the temperature dependence on resistance. So let us learn just by comparing from the expression, same expression, that RT is equal to R naught into 1 plus alpha into T minus T naught, then R naught plus alpha into R naught T minus T naught. So RT minus R naught is equal to alpha into R naught into T minus T naught, and let us find out the expression for alpha is equal to RT minus R naught divided by R naught into T minus T naught. So we have now learnt what is alpha, that is temperature coefficient of resistivity. Based on the resistivity, it is rho T minus rho naught divided by rho naught into T minus T naught, that means delta rho by rho naught into delta T. Here alpha, based on resistance, it is alpha is equal to delta R, that is change in resistance divided by R naught into change in temperature. So this alpha is nothing but temperature coefficient of resistance, and this definition, define temperature coefficient of resistance, is an often frequently asked question. How will you define this? From the expression we can define. Alpha is defined as, that is temperature coefficient of resistance is defined as increase in resistance per degree rise in temperature to the resistance at T degree, T naught degree, to the resistance at T naught, that means at a reference temperature. So here it has the same unit like per degree Celsius. Now it's our topic to learn what is alpha for semiconductors. So far we have learned the alpha for conductors is positive, and based on that we learn if we increase the temperature, resistivity also increases in the case of conductors. It is because of they undergo more number of collisions, and so its the resistivity increases. Now coming to the alpha for semiconductors. The semiconductors, when you take, if you increase the temperature of the semiconductor, the resistivity decreases. It is because the semiconductors has at room temperature only less number of electrons, but if the temperature is raised, then it gets abundant number of electrons, they undergo collision. As the number of electron increases, its resistivity automatically decreases, and that is why this alpha for semiconductors is negative value. Alpha for semiconductors is a negative value. Any semiconductor with negative temperature of negative temperature coefficient of resistivity is called thermistor, and we have been given in our exercise problem number 4 to find out what is the resistance, to calculate the resistance at the boiling point of water of nichrome. You know what is nichrome? Nichrome is an alloy made up of nickel, chromium. See, this you are given, you may just refer problem number 4 from exercise, page number 124. You are asked to calculate what is the resistance at 100 degree Celsius. We can use this expression what we learned previously. This expression can be used to find out. Okay. So, first this is problem, you may just refer, it is problem number 4 in your exercise. That given data you must write. Resistance is at 0 degree Celsius is given as 10 ohm, and alpha is given, and you are asked to find out R100, and reference temperature is given as 0 degree Celsius, and temperature, boiling point temperature is 100 degree Celsius. So, let us substitute the values. 10 into 1 plus alpha is 0.004 to 100 minus 0. So, from the given data, resistance at 0 degree Celsius is 10 ohm, and alpha value is given. You are asked to find out what is the resistance at 100 degree Celsius. So, we have the expression previously, RT is equal to R naught into 1 plus alpha into T minus T naught. When you substitute the values and we calculate, it is found out that resistance at 100 degree Celsius is 14. What do we comment on the result? What is your comment on the result? Just when you see resistance at 0 degree Celsius is only 10 ohm. But if the temperature is raised to 100 degree Celsius, now you find that resistance also increases. Here in this problem, you are asked another question that comment on your result. So, you should not leave with only the answer, you should also comment that when the resistance, you may find that when the temperature increases, the resistance also increases. Okay. Now, let us come to the table. You are given a table showing resistivity of various materials, right from all metals, alloys and semiconductors. You see each metal, when you take these metals, they have different temperature coefficient. Metals, they have temperature coefficient alpha. Just observe for nichrome, you see it is 0.4 into 10 power minus 3. What do you infer from this? You know, nichrome is an alloy. Nichrome is an alloy. It has weak dependence on temperature. Not only nichrome, it is also constantan and manganese. They are insensitive to temperatures. So, their alpha value is independent, almost independent. So, its value is very less. This is the reason why nichrome, constantan, manganese, they are all used in wire bound resistors. So, after our observation from the table, all these metals and alloys, they have positive alpha value, and other semiconductor materials like germanium, silicon, carbon, they have negative alpha value. And this same temperature dependence on resistivity, and especially temperature coefficient of resistivity, it can be explained in another way also by recalling what you have learnt in the previous section, the expression for sigma. What is sigma? It is conductivity. So we know that sigma, it is given by the expression n E squared tau by m. Sigma is the conductivity, and it's a very known fact that resistivity is the reciprocal of conductivity, and so we can write that resistivity rho is equal to m by n E squared tau. And this n is number of density of electrons, and tau is the average time of collision between electrons. See, let us take for a conductor, suppose if you increase the temperature, already conductors, they have more number of electrons, their average kinetic energy also increases, that results in more number of collisions, and thus why it reduces its tau value, and thus resulting in the increase of resistivity in the case of conductors. If it is semiconductors, if you increase the temperature, that results in the more number of electrons, number of n increases, but at the same time there will be decrease in the tau value, but increase in n value, that is increase in the number of density of electrons is dominant. That is why resistivity of the semiconductor decreases. But in the case of conductors, you should remember that temperature does not affect, or temperature affects in no way the number of electrons present in the conductors. It happens only in semiconductors that if you increase the temperature, automatically n increases, that even though it results in the decrease of tau value, increase in n is dominant, that is why its resistivity decreases. So this is another way of giving explanation how the resistivity is dependent on temperature. So what's the practical use of this learning, this topic? So it's wonderful fact that superconductivity. Hope you all heard about maglev trains in Japan, which is based on the principle of superconductivity. Superconductivity is nothing. When temperature becomes very low, and the resistance of certain materials becomes zero. When the resistance becomes zero, automatically its conductivity becomes infinity. Conductivity is infinite. So that the lowest possible temperature where the resistance of certain material becomes zero is nothing but critical temperature or transition temperature. And it was Kamerlingh-Onnes, name of the scientist Kamerlingh-Onnes, in the year 1911. He found out that it was mercury at 4.2 Kelvin. It is the lowest possible absolute temperature of mercury. Mercury completely loses its resistivity. Resistance becomes zero and it becomes superconductor. Conductivity, the current is induced here, it lasts even though there is no potential difference, and this principle is nothing but, or this phenomenon is called superconductivity, and the materials which exhibits such a superconducting in nature, or which exhibit superconductivity, are nothing but superconductors, and mercury is one of the best superconductor.